Lab 2 report. So the purpose of this lab is to compare the position of a projectile affected by the forces of gravity and drag using an experimental and computational model. My object was a tennis ball, experimental model was a tracker app, computational model was glow script. So first principle is the momentum principle, which is F net is equal to the change in momentum. We threw the tennis ball like this, so F drag is going opposite to the direction of motion, and the force of gravity is going in a negative y hat direction. So F net will look something like this. Newton's first law. So an object in motion will continue with the same speed and same direction unless acted on by an unbalanced force. And we have the force of gravity and the force of drag. The force of gravity is only affecting the y component of motion. So that means the x component is going to be constant. The x velocity is going to be constant. But the force of drag not only affects the y component, but also the x component. We'll see more of this in our computational model. These are all of the formulas we're going to be using in our computational model. Lab procedures. We're going to capture a video of the tennis ball in projectile motion, measure the mass of the tennis ball, and spoiler, the mass was 0.04 kilograms. We're going to import the video and tracker, get that data from the tracker app, and use it as the initial conditions in GlowScript to create two GlowScript computational models. One will take into consideration the force of gravity, and the other will take into consideration the force of gravity, along with the force of drag. And we're going to compare all these trajectories with all the models. So here, this is our tracker video. These are our tracker data right here that we're going to use. This is the calibration stick, and our axis is aligned with the floor. So we're going to get our initial conditions. That's the total time. That's the change in time. Initial position, initial velocity. And we found this by getting this position vector, subtracting it by this position vector over the change in time to get initial velocity, meters per second. So the main difference between these two models is that this has 0 as a proportionality constant because we're only considering the force of gravity here. But this has a value because not only are we looking at the force of gravity, but we're also looking at the force of drag. And the reason why I got this number was because it accurately reflects my tracker model. And these are the while loops. The main difference is F net is equal to the force of gravity. But here, F net is not only the force of gravity, but the force of drag. And the force of drag was calculated right here. So our output with no drag force. So we're only looking at gravity, the force of gravity. Once again, the force of gravity acts only in the y hat direction. Sorry, the negative y hat direction. So that's why our velocity in the x direction is constant, meaning that there are no forces in the x component of velocity. But here, there is a negative y hat component, which is affecting the velocity, and that's why it's changing. Here, we're not only looking at gravity, but drag, and that's going to affect the x component of velocity, and that means there is a force in the x component of motion. So these are all the trajectories from all of our models, the tracker and both the computational models. So some errors, maybe when I'm clicking, when I'm clicking in tracker, I'm not aligned exactly with the point by mass. Also, my calibration stick may have not been perfect. So there could have been some errors with the tracker app. And in terms of the real world, it's not just gravity and drag force. There's other forces that may have not been considered. Oops. What does it mean for my model to show terminal velocity? Terminal velocity is when the forces, they're all balanced out. So F net is 0. And none of my models show that. But we could design an experiment where we drop an action figure with the parachute, and the drag force will be exactly the same as the force of gravity to make it the action figure have terminal velocity. So what if the tennis ball was thrown straight up with the same speed? So would it take longer, shorter, or the same amount of time for it to hit the ground? It will actually take longer Because in my experiment, we threw it at an angle, and sine could reach a maximum angle of 1. So that means it could be less than 1. And when you're multiplying something less than 1, it's going to decrease its value. And so it'll make time smaller than if I was just to throw it straight up. Thank you.